So I'm recording now. And we're starting with 7. We answered already the first 4 parts, and we're doing the 5th part, which is how many CDs cost between $14.50 and $26. I would say 6 CDs. Does anyone know how do I come up with the answer? It's 6. And let me explain to you why. Okay, look here, guys. 1450 is the Q1. 26 is the Q3. Q1 is 25th percentile. Q3 is 75th percentile. The difference between 25% and 75% is 50%. It means, guys, that 50% of the data lies between Q1 and Q3. Well, 50% of 12 CDs is 6 CDs. So it is 50% of 12. For your information, guys, from here to this right there is 25%, because that's the beginning of the data set until the 25th percentile. Then from here to the median is 25%. And from the median to the third quartile is 25%, and this is another 25%. So your box plot is split up into 4 pieces. Each is worth 25%. Then that's going to make it easy to answer how many CDs cost less than $14.50. Well, $14.50 is right here, guys, and less there will be the first quarter. So it's a quarter, 25% of 12, which is 3 CDs. And think about it, guys. 3 CDs here, 6 CDs there, that's 9, and then another 3 there, that's 12. That will give you the whole thing. Okay, next question. A movie theater recorded the number of tickets sold daily for a popular movie during the month of June. The box and whisker plot shown below represents the data for the number of tickets sold in hundreds. Which conclusion can be made using the plot? Tell me if this is true or false. The second quartile is 600. True or false, guys?
False.
False, because the second quartile is 400. The mean of the attendance is 400. Is this true or false? We don't know the mean, guys. The box plot doesn't have the mean. It has the median information, so that's false. The range of the attendance is from 300 to 600. That's not true. The range starts from 100 all the way to 900, so that's false. So it must be, guys, that the last one is correct. 25% of the attendance is between 300 and 400. Watch, guys. I told you, the box plot is split into 4 pieces. Each is worth 25%. So this piece by itself is 25%, which is true. All right, let's go and do the next one. This is a nice exercise, guys. Please pay attention to it. You can say a lot about the data set from the box plots. Okay, the box plot can be used to compare the annual incomes of 3 professions. So we have the box plot for the musician income, police officer income, and nuclear engineer income. Based on the box and whisker plots, which statement is true? So let me put the statements close to you here. All right. Let's see which one is true. It says the median income for nuclear engineers is greater than the income of all the musicians. True or false? Median income of nuclear engineers is greater than the income of all.
False.
That's false, definitely, because look, this is the median income, guys. And these are the musicians. Some of them make more than the median income. They're here, so they're more. So that's false. The median income for police officers and musicians is the same.
True.
True, because the median income for police officer and musician is 30,000. Yeah, that is true. Look, it's right there. It's the same. Okay. The rest of them, definitely they're false because we got the true statement. And then the last one. That should be an easy one. Use the stem and leaf plot to find the median. Okay, you have a stem and leaf plot. You need to find the median. How many values do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So your median, guys, if you want to find the median, it's divide 16 by 2, you get 8. So it's between the 8th and the 9th. One way to do it, you can list the values and figure it out. But there is another way, a faster way, guys, you can figure out. Count to the 8th and 9th value. This is the first, second, third, fourth, fifth, sixth, seventh, 8th value, which is what, 79. And 9th value, guys, which is 81, and find the average of the two. And that should be your median. I was doing this exercise with a student yesterday during office hours. We listed the values and we figured out the median. So this is another way to do it. All right. So that concludes chapter 2. And we're gonna begin with chapter 3. It's a new chapter. Okay, so that's chapter 3. It's an introduction to probability. We need to know probability, guys, because there are so many things that we do in life that we're not sure about. So we just have to make predictions. And when you make predictions, you need a reference to probability. Even the weather forecasting that you hear of every day, it's a prediction. It is based on information, sometimes guesses, intelligent guesses. So it is a probability. When we know that things for sure are happening, we don't need a probability. When you are certain of an action that it's going to take place, you don't need to do probability. So we do probability because we are unsure. And that's why we have to determine the likelihood that something will happen using probability. What I like you to do, guys, I used to do this in class, but since we're doing it online, I think it's going to take a lot of time to do it. And maybe some of you don't have access to dice, but if you do, if you have a couple dice at home, I would like you to do this experiment and we'll discuss the results tomorrow. I would like you to roll the 2 dice together about 40 to 50 times and record the sum of the numbers that come up on the faces. Let's say you roll a dice and you get a 2 face up and a 3. So 2 plus 3 is 5. And then once you get a 2 plus 3, 5, you just gray this one in here. Just put a 5 here. Then you roll again and let's say you get 3 and 4, 7. Then you roll again and you get a sum 6 and 5, 11. Then you roll again and you get 5 and 6 again, something like that. Just do this if you can. If you have 2 dice at home, I would like you to do it. It should take a few minutes only. And then I'll ask you today, what kind of graph did you get? What was the shape of the graph that you got? But I can tell you guys something from now. It's very unlikely that you're going to get as many here, 2 and 12. Because in order to get a 2, you need 1 and 1. And that's not gonna, you're not gonna see it a lot. And in order to get a 12, you need 6 and 6. 6 plus 6 is 12. That's not gonna happen a lot. A lot is gonna happen right here. So if you have 2 dice, do it. If not, it's not a big deal. But I'll do mine today and I'll share some results with you tomorrow. I'll show you what my graph would be like tomorrow, okay? Probability. Let's go to the definition of probability. Any questions, guys? Interrupt me at any time, send me a text or unmute yourself and talk to me. The probability experiment is an action or a trial through which specific results, counts, measurements, or responses are recorded or are obtained. For example, you roll a die. That's a probability experiment. Now, what are the possible outcomes or the possible actions that you would see? You could see number 1, you could see 2, you could see 3, 4, 5, 6. You don't have control of this. An outcome is a result of a single trial in a probability experiment. For example, I just stated that. If you roll a die, what are the possible outcomes? You could see 1 face up, 2 or 3 or 4 or 5 or 6. What is a sample space? Sample space is a collection of all the outcomes in an experiment. So if you toss a coin, guys, a quarter, what are the possible outcomes? You could get a head or a tail. Your sample space consists only of 2 elements, either a head or a tail. What is an event? An event consists of 1 or more outcomes, and it is a subset of the sample space. For example, let me give you an example of an event. You roll a die. You would win if you get an even number. So what are the possible numbers that you should get on the die in order to win? If you get 2, you win. If you get 4, you win. If you get 6, you win. That's your event. So here is an example. Probability experiment. Roll a die. That's an experiment. Outcome, you might roll a die and get a 3. That's an example of an outcome. The sample space, guys, is all the possible outcomes. When you roll a die, it has to be not a loaded die, a fair die. You could get a 1, a 2, a 3, a 4, a 5, and a 6. An event, you play the game. You win if you get an even number. So your possible numbers that would help you win are 2, 4, and 6. Okay, any questions here about those definitions? All definitions, guys. A probability experiment consists of rolling a die and tossing a coin. Describe the sample space. Can you guys help me list all the outcomes when you do 2 actions at the same time? We're rolling a die and tossing a quarter. What would you get? What are the possible outcomes if you do that? I'm gonna list them. Start with, can you tell me what would be the first one of the outcomes? There are too many. What could you get if you roll a die and toss a coin?
Tails.
What is it?
Oh, you can get heads and tails for the die. You can get like
1, 2, 3, 4, 5, 6 for the die, you mean, and then heads and tail for the coin, right?
Yep.
But put them together because you're doing it together. So, because you're seeing 2 actions at once, 2 things are happening at once. So, what would you get first? What would you see? 2 and exactly. Students, a head with a 1, a head with a 2, a head with a 3, a head with a 4, a head with a 5, a head with a 6. But you could get a tail with the 1, tail with the 2, tail with the 3, tail with the 4, tail with the 5, tail with the 6. Can you count them for me, guys? How many? 1, 2, 3, 4, 5, 6 times 2 is 12. Okay. There are 12 outcomes in this experiment. This experiment consists of 12 outcomes. Okay. Let's do an example, another example. Toss 3 quarters. List all the outcomes. Can you help me list them, guys? Start with the first one. We're tossing 3 quarters at the same time. So when you observe the face up on all 3 quarters, not just one at the time, all together. So would you guys agree with me? It is possible to get head, 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 or it is possible to get head on the first one, head on the second one, tail on the third, or head, tail, and then head, or head and tail. That's 4. Then you could get tail, tail, tail. Yes. Then tail, tail, head. Then tail, head, tail. And then tail, head, head. And now, guys, I can challenge you. It's impossible to come up with more. That's it. 8. That's what you could get. There are no more than 8 outcomes. And we'll know why and how can you be so sure that there are only 8. You don't have to think of any more in a second, just in a minute. A simple event. A simple event has only one outcome. So if an event leads only to one outcome, guys, that's called a simple event. Most events, guys, lead to more than one outcome, but there is a definition of simple event. Okay. Now, let me show you guys here that if I ask you how many outcomes there, you really didn't need to list them. You could have figured this out without even listing them. And I'm going to show you how. If you roll a die, there are 6 outcomes. If you toss a quarter, there are 2 outcomes, head or tail. Look what you can do, guys, simply. Just multiply 6 by 2. What is 6 times 2? 12. There you go. Look here. I tossed 3 quarters. I need to figure out how many outcomes. I really don't need to list them to figure out how many. Each quarter has 2 outcomes, 2 times 2, two outcomes, head or tail. Well, I have 3 quarters, guys. 2 times 2 times 2. What is 2 times 2? 4 times 2, 8. Here you go. And now let me ask, if you roll 2 dice, what are the possible outcomes? So you're doing, 2 things at once. How many outcomes are there without listing them? Can someone tell me? That's easy now after we did those 2 examples. You multiply 6 by 2. That's not true. 6 times 2 will give you a die and a quarter. What else? 36. Yes. It is 6 times 6, guys, because the first die has 6 outcomes. The second die has 6 outcomes. 6 times 30 times 6 is 36. You don't believe me? Let me start listing them. 1 with 1, 1 with 2, 1 with 3, 1 with 4, 1 with 5, 1 with 6. That's 6. 2 with 1, 2 with 2, 2 with 3, 2 with 4, 2 with 5, 2 with 6. That's another 6. 3, 1, 3, 2, 3, 3. They come in pairs, guys. 3, 1, 3, 2, 3, 3, and so on. You get 36. So 6 times 6 is 36. Here is the principle, guys. There is a principle that you can use to figure this out. If one event can happen in M ways and another event can happen in N ways, like in Nancy, the 2 events together can happen in M times N ways. You don't add, it's multiplication. 6 times 6, 6 times 2, 2 times 2 times 2. This is how you figure out the number of outcomes. We're going to do an example here to demonstrate, this principle, the fundamental counting principle. Look at this example. It's an easy one. You are purchasing a new car. You can buy a Ford, a GM, or a Honda. You can buy either a compact size or a mid-size, or you have choices of colors, white, red, black, and green. In how many ways you can buy your car? What are your possible choices of your car? I don't want you to list the choices because it's a very long list. Students can say, well, I want to buy Ford that is compact, that is white. Another one, I said, I want to buy a Ford that is mid-size, that is red, and so on and so forth. Rather than trying to list all of them, guys, let's try to figure out how many choices do we have. We're going to use the principle right here. Okay. For Ford, for the car make, we have 3 choices, guys. So you just put a 3 here. 1, 2, 3. For the size of the car, I have 2 choices. For the color of the car, I have 4 choices. And can students tell me what operation do I put in between here? Don't be shy, guys, of participating. I'll correct you. Yes, it is multiplication. You see, that's multiplication here. That's a possible question on your next test. See something like that, and that's how you answer it. That's the answer. Here's another example, guys. A pizza place. They have two different crusts, two different types of crusts. You can choose one of the two. They have 3 different types of cheese, so you can choose one cheese out of the 3. And then they have 10 different topics. You can choose one topping. How many choices do you have? How many different pizzas you can order? So you just take the 2, multiply by the 3, and then multiply by the 10. 60 possible combinations of pizza. That's how you do it. Exactly, it is 60 as you said. Okay. Probability, definition of probability. Probability, guys, is a percent. It will never exceed 100%. It's always between 0 and 100%. And here is the theoretical classical definition of probability of an event. It is number of favorable outcomes divided by number of all possible outcomes. Denominator is always bigger than the numerator. Favorable means the outcomes that work in your favor of the event that you want to happen. Possible is everything. Let's do an example and show you how to use this definition to find the probability. You roll a 6-sided die. What's the probability of rolling a 3? And this is called event A. So you can write it like this. Probability of A equals. Okay, guys. How many possible outcomes do I have when I roll a 6-sided die? Possible outcomes means what you cannot control. You don't know what's gonna show face up. So we have 6 possible outcomes. It could be 1, it could be 2, 3, 4, 5, or 6. But on the faces of the die, how many 3s are there? Can the student tell me? I'm sure you know about the die. There's only 1, you're correct. So your chance of winning is only 1 out of 6. What's the event of rolling a 7, guys? It's always 6 at the bottom. Who knows the answer? Is there a 7 on the face of a die? 0. Yes, I agree. You cannot get a 7, that's impossible. So if someone invites you to play this game, don't play it because you know you're gonna lose every time. Rolling a number less than 5, that's event C. Well, the denominator, guys, doesn't change. It's always 6. Okay, what are the faces on the die that are less than 5? You could get a 1, a 2, a 3, a 4. So it's 4. 4 out of 6. And one thing I'd like you to know, guys, here, I don't care what the outcome is. I only count how many. So don't ever think of what the actual outcome is, just how many are there. Less than 5, I know 4 is less than 5, 3, 2, 1, there's 4 of them, that's all I care about. So this is the classical definition of probability. We're gonna give you another definition of probability. It's called the statistical definition of probability. Very much the same as the previous definition, but I'll write it differently. When you have a frequency table, how do you use it to find the probability? So the denominator is the sum of all frequencies, and here is the frequency of the event. Frequency of the event means how many times did the event happen. And let me show you how to use this definition, guys. Very easy formula. A company is conducting a telephone survey of randomly selected individual to get their overall impression on the past decade. So far, 1504 people have been surveyed. What's the probability that the next person surveyed has a positive overall impression? So we need a probability of positive impression. When you write the letter P, guys, it's usually capital. And can the students tell me how to figure out what is the sum of all frequencies here when you have a table? It's right here. Okay, and what should go in the numerator, guys? 406, I agree. You are correct. That's the answer. You're done. Both the classical definition of probability and the statistical definition become very much the same when you have so much in your data set. It's called the law of large number. So when you repeat an experiment over and over, both the statistical and the classical definition become pretty much the same. Okay, let me tell you about another type of probability that we're really not very much interested in, but you need to know it. Actually, it does exist. Sometimes you make your probability based on an intelligent guess or intuition. Here's an example. So you don't do any math, you just try to figure it out based on past experience. A doctor may feel a patient has a 90% chance of full recovery. This is based on an intelligent guess. How does the doctor know it's exactly 90%? The doctor will go back and look at his records and think that from the patients who had the surgery, from 100 patients, 90 had a success. So he just make the prediction that it's 90%. So this is not it's based, just on educated guesses. Weather forecasting, it's based also on fact and sometimes, just educated guesses as well. Predicting the market, guys, the stock market, it's very much based, just on educated guesses as well. Otherwise, if this is a fact, everybody will go and invest in the stock market if the information that they receive, they know it's 100% accurate. They tell you they predict the stock is going to go up by 5 or 10%. That could happen, but it is possible that it doesn't happen. So that is an educated guess. What we're going to do in this example, guys, I have 3 examples. I like them to match them either as a classical, statistical, or subjective. What do you think of the first example? The chance that you will get the flu next year is 0.1. Is this a classical based on a formula or experience or a table or a subjective? Do we have an answer? I hear subjective. I agree. Yes. This is just an intelligent guess. How do you know that my chance is 10% next year that I'm going to get the flu? It's based, just on past records, intelligent guesses. The probability that a voter chosen at random will be younger than 35 years is 0.3. Remember, voters means the survey, somebody collected data, put them in a table, organized them. So that is, guys, it's going to be what? Empirical. I agree, Julia. Now, the probability of winning a raffle ticket. You have a raffle, 100 numbers. One of them is a winning number. They're going to withdraw one number, which is the winning number. This is very much the typical classical definition of probability. Favorable outcomes. There's one winning number. So you have one number in your favor to win, but there are other 100 numbers that are the possible outcomes. Any number could come up. So this is a classical. Anything, guys, that doesn't require a table, a frequency distribution table, is a classical definition of probability. Okay, for your information, the probability can never exceed 1. It's always between 0 and 1. So one thing you never want to do on a test to give me an answer that goes beyond 1 for probability. That's impossible. I would rather that the students does nothing there rather than putting an answer of more than 1. I'll share this exercise that I gave probably last semester to students. I said, is this a true or false statement, and justify your answer. A student is making 120% efforts to pass the class. If this statement is true, just say why. If it is false, say why. What do you guys think? Can a student make 120% efforts in the class? What do you guys think? It is false, definitely. You cannot go beyond 100% capacity. Your capacity is 100%. So this is false, and easily you can just tell me that because it's over 100%. That's it. Okay. Let me explain now the next one. What's a complement? The probability of rain, let's say, is 0.68. What is the probability of no rain? Can someone tell me, how would you figure this out? If I give you the probability of rain, you should be able to figure out the probability of no rain. Okay, good answer, 0.32. A student said it's a 0.32, and this is correct because both of them should add up to 100%, guys. So the way that students figured it out took 100% and subtract 68%. That is correct. So here's the conclusion, guys. Probability of event E plus probability of not E, together they should always add to 1. The not E is called E prime in the textbook. So here, probability of E prime plus probability of E, guys, should always add up to 1. So this is a possible question on the test, guys. He'll tell you the probability that the students will pass the class is 70–80%. What's the probability that students will fail the class? You could figure it out. It's 100% minus 78%, which is 22%. So it is, once you know a probability of an event happening, you know what the probability that the event will not happen. You can easily determine that using this formula right here. Okay. Let's do the next question example. If I'm going too fast for you guys, let me know. I can slow down a little. You survey a sample of 1,000 employees at a company and record the age of each. What's the probability of randomly selecting an employee whose age is not between 25 and 34? All right, guys, I'm ready. How would you figure this out? If you pick one, there are 1,000. Guys, I'll make it easy for you. Denominator is 1,000. What's the chance of selecting an employee at random, put all those names in a basket, and pick someone who is not between 25 and 34? So I see a student saying that you subtract the 366 from 1,000, which is correct because we don't want the age 25 to 34. We want anything but the age 25, 34. You are correct. That will be 1,000 minus 366. Yes. So it will be 634 over 1,000, which is 0.634. So that's the complement, guys. 100% minus the one that we don't want. Another way to do it, I did this morning. A student says 54 plus 233 plus 180 plus 125 plus 42 divided by 1,000. I say that's correct too. You can do it this way, but that's faster that way. Okay, next question, guys. Help me with this one. Your college identification number consists of 6 digits. One, two, three, four, five, six. Okay. Each digit can be 0 through 9, and digits can be repeated. So you can have an ID number, let's say 110156. It can be anything here. What is the probability of getting your college identification number when randomly generating 6 digits here? I'm sorry. Should be 6. So guys, what is the probability? You go to your calculator and you ask your calculator, let's say this is your ID, guys. Let's say this is your ID. That's your ID number, 6 digit. What is the probability? What's the chance that you're gonna tell the calculator to generate a 6 digit number and it's gonna turn out this one? It's just like dreaming. This is a dream, guys. It's not gonna happen. Just like winning the lottery. It's very, very low probability, but how do I figure it out? Any suggestions before I go through the answer? First of all, I need to figure out how many possible IDs are there. You need the possible outcomes, guys. Let's try to figure it out. For this digit here, how many possible ways you can put the digit? He says anything from 0 to what? To 9. How many are there from 0 to 9? 10. Same thing here. Same thing there. And what do you do, guys? Remember, multiplication is the key here. So you have 1, 2 million. Okay. One more. Okay. What's the numerator, guys? You have a unique ID. Nobody else can share your ID with you. It's your unique number. So what's the numerator going to be? Somebody make an input. 1, I agree. This is your the chance of this happening, guys. It's 1 out of a million. So it's not gonna happen. Very likely it will not happen. If you just go, if you know your ID number, guys, and you go to your calculator, there is a way for a calculator to generate a 6-digit number. There is a program. You're not gonna see your ID, guys. That's not gonna do it. Just like thinking of winning, you know, just the Powerball. You know, that's unlikely. It's very sure it's not gonna happen. The chance of this happening is very, very, very low. Okay. Before I do this, let's do that one. I'm gonna do another exercise talking about the law, fundamental counting principle. The state of Michigan license plate. I think, guys, it is 3 letters and 4 digits. I don't know. I have to go and look outside. Is it 3 letters and 3 digits, guys, or 3 letters and 4 digits? Let's assume it is 3 and 4. I want to figure out if the state of Michigan has enough license plates, you know, for years to come. So I want to figure out how many possible combinations of license plates. You know, they cannot give the same license plate to 2 current vehicles. They have, once one expires, yeah, they give it back to somebody else, but not at the same time. So I want to figure out how many license plates are available now at the state of Michigan and see if we're good for years to come. This is a letter. How many possible ways to put a letter there? There are 26 letters, so that should be a 26. You know, letters and digits can be repeated on the license plate. So there is a 26 here. There is a 26 there. But for the digits, it's a 10, 0 to 9, 10, 10, 10, 10. You want to figure out how many license plates? Let's do the multiplication. Okay, let me do it with you guys. 26 times 26 times 26 times 10 times 10 times 10 times 10. Okay, what do we have? 175,760,000. Do you think, guys, we have enough? Well, the state of Michigan is only 10 million people, so we still have a lot of license plates, you know, available for years and years and years to come. That's how they figure it out. See how strong this law that you learned, you know, just a fundamental counting principle. You don't add, you multiply those numbers, and you figure out the possible outcomes. Okay, conditional probability. We're going to learn about conditional probability today, but before I get into this, I want to show you this table that I'm going to use to explain conditional probability and make sure that you understand how to read this table. This is a table about children with high IQ, normal IQ, who has a certain gene present that could affect, you know, their IQ. So the table shows the results of a study in which researchers examined a child's IQ and the presence of a specific gene in the child. First of all, guys, I'm gonna just start circling numbers and ask you to tell me if you know how to interpret what this number is about. What does 52 mean in the table? Look at it. You need to know it before you answer any question.
That's the total IQ of this.
Total high IQ, exactly. What about 102? It looks like 72 plus 30 is 102, 52 plus 50 is 102. This is called the grand total, guys. It's total number of children surveyed. Okay, another question. What does 72 mean? Can someone tell us what 72 refers to? Kids without the gene or with the gene? With, I agree. You're right. It's total number of kids, children with the gene. Okay, one more, just to make sure that students get the idea. What does 11 represent? Someone type it in and I'll correct you. Normal IQ and no gene present. So the plus, your plus means and. Yes, it's together. Someone who has a normal IQ and the gene is not present. Together. Yes. Okay. Let's go back and define conditional probability, guys. All right. And usually if I give you any questions about conditional probabilities on the test, it will be in the table format, guys. So once you understand the table now and see how we're gonna answer the questions, you just mimic, you know, the experience from today to answer the questions. Okay. Conditional probability. It's the probability of an event happening given that another event took place already. So that's what the condition is. He'll ask you to find the probability of something happening given that something else has happened already. Probability in general, no. He'll ask you to find the probability of an event, but conditional, what is the probability of A happening given that B has happened already? So, and I'm gonna show you how to deal with this. Before we do the part A, I wanna go to part B. It's a easier one. It doesn't have any conditions there. What is the probability of selecting a child at random with normal IQ? So you have 102 children. If you select one child at random, what's the chance that you will be selecting someone with normal IQ? Okay, it's a fraction, guys. It has to be a fraction. Let's see if we have any answers. Okay, I got 50 divided by 102. Do you guys agree? And please, if you don't agree, let me know so then I can explain it. It is correct. I have 102 children. These are all the outcomes. And now the numerator should be the favorable one. Remember, favorable means the ones that you want to happen. Well, we want the normal IQ. And you are correct. The normal IQ is 50.
Oh, Taylor.
You're sort of cool yourself.
Okay, guys, 50 divided by 102. Now, some students might say 39, but well, 39 is not all the normal IQ. It's a normal IQ with the gene present. Another student say 11. Well, 11 is normal IQ with gene not present. We want all normal IQ, regardless whether the gene present or not present. So it is 50. Okay, let me ask another question that I didn't put there before I proceed to A and C. What's the probability of selecting a child with gene present?
72.
72 divided by
10.
102. Yes.
Okay.
What's the probability of selecting a child who has gene not present? It will be 30 divided by 102. Okay, let's go to A. This is the new stuff, conditional. And I'll tell you how do you know that this is conditional probability. Find the probability that the child has high IQ. If they stop there, guys, that's an easy answer. Just high IQ, I have 52 divided by 102, but that's not what it says. Find the probability that the child has high IQ, given that the child has a gene. So he's imposing a condition on us that he wants the child to have the gene present. What would be?
33.
So let me write it down. High IQ. Okay, for given, guys, they write it in the book like a vertical line. Once you see a vertical line, that's a given. Gene present. All right, I'm ready for feedback on this. Input your answers, guys. Don't be afraid if it is wrong. I'll correct you. I'm here to support you. So let's participate. I need to see more participation because later I'm gonna put you in breakout sessions, guys, and just do some participation work. So let's participate and see what you get. So what do you guys think? What's the probability of someone have a high IQ given that the gene is present? What's a numerator and what's a denominator? Okay, I got 33 over 102. What do you guys think? 33 divided by 102. $33 divided by 72. Oh, here you go. Answers are changing. Okay. What else? One of the answers is correct. So it is 33 divided by 72, not 102, and I'll tell you why. Let me write it down, then explain it. Okay, guys, he put a condition on us. He says, given that the child has a gene, so we don't have a choice to select from the entire group of children anymore. He says, I want, whatever probability you're doing, I want it to be out of the group of students who have the gene. How many total do we have that have a gene here? It's 72. So you put 72 in the denominator. The 33 is easy, guys. High IQ and the gene present. Look, this is the gene present, and this is a high IQ. Where do they meet? They meet at 33. So it is 33 out of 72. This is the trick that I gave to my students this morning to figure the answer out. This is what I told my students. I told my students whatever statement comes after given, that will be your denominator. So what comes after given, guys? The child has a gene. So you just go and count the total of the gene present and put it in the denominator, which is 72. It goes 72. For the numerator, guys, it's very easy. The numerator, you just, the vertical line gene present, the horizontal line high IQ, where the two meet, intersect, that will be your number. So it's 33 divided by 72. Let me do part C and see, guys, if what I said can be applied in part C. What is the probability that a child has the gene given that the child has high IQ? So we're reversing here. Okay, guys, can you give me an answer now?
Would
That
it
should
be
be-
72 over 33?
No, we want the high IQ to be here. How many high IQ are there? What's the total? 52. And here it will be the same as right here, 33, because high IQ and gene present will be 33. Does that make sense, guys? Gene and high IQ, it's the intersection. That does not change, it's 33. But now he says, I want you to pick from the group of children who has high IQ, not the 102, so that the group of children who has high IQ is 52, guys. So it's 33 out of 52. I'm gonna put a part D, and then I'm gonna give you a minute, guys, all of you to answer it. And just to make sure that we understand this. D, what is the probability that a child has normal IQ given gene not present? Okay, I'll pause for a few seconds, guys, and let's put the answer here. So the probability a child has normal IQ given that the gene not present. Remember, what comes after given goes to the denominator. Ten more seconds, and I hope that your answer will match with mine. Let's see what we have here. You can input your answers, guys, in the chat. 11 over 30, and I got 11 over 50. Given that the gene not present, the total of gene not present is 30. That is correct. And how many are there who have a gene not present and normal IQ? It's 11. So it's 11 over 30. All right. This is conditional probability. We'll have a chance to do a little bit more on conditional probability later in the practice exercises at the end of this. Now I'm gonna tell you what independent events are, guys, and give you some examples of independent events. Two events are called independent if the occurrence of one event does not affect the chance or the probability of the second event. So that means if the first event occur, the second one will occur without any interference, just from the first event. If this is the case, then you can say the events are independent. If this is not the case, then you can say the events are dependent. Let me give you an example. Decide whether the events are independent or dependent. If you have a standard deck of cards, guys, it has 52 cards. There are 4 kings and there are 4 queens in there. He says, your first event is to select a king from a standard deck of cards. Can someone tell me what's the probability of selecting a king from a standard deck of cards? You have 4 kings there.
4.
What would be the probability? Yes?
4 out of 52.
4 out of 52. All right. What's the probability of selecting a queen?
4 out of 51 then.
No, in general. In general. It's 4. It should be 4 out of what also? 52. But you're right here. You select a king from a... So if they don't interfere with each other, the 2 events, we should get the probability of a queen to be 4 out of 52 because that's what it is. If you open a standard deck of cards, guys, you're going to see 4 queens out of 52 cards. So your probability is 4 out of 52. But look what it says here. You select a king from a standard deck of cards. That's a probability 4 out of 52. You don't replace it. So you pick up a paper, but you don't put it back. And now, guys, you don't have 52 cards to work with. You have 51. And the student was right. She says the probability now is selecting a queen is not going to be 4 out of 52. It's going to be 4 out of 51. And that's a violation to the classical definition of probability, which should say, it says it should be 4 out of 52. That means the first event, guys, event A had influence on event B. That means the events are dependent. All right, so this is what dependent and independent. Now look at the next one. You toss a quarter and get a head. That's one first event. You roll a die and get a 6. Do you think the events are dependent or independent? Do they have to do anything with each other? The probability of a head is 1/2. The probability of getting a 6 is 1/6. And you guys, these are 2 different actions, 2 different experiments. They have nothing to do with each other. These events are independent. But now I'm going to give you some more exercises to give you a good feel of dependent and independent events. We're going to go to the book. It's on page 153, guys, if you're taking notes. Exercise 9 to 14. It's on page 153. You can see number 9 I've already done, guys. What about 10? First event is returning a rented movie after the due date. And the second event, if you receive a late fee. What do you think of the events? Definitely dependent, because as a result of being late, you were charged a late fee. This is an example of dependent events. 11. A father having hazel eyes and a daughter having hazel eyes. What do you guys think? Are they dependent? Yes, dependent. I agree. Next one. Because the children can take after their parents, as far as eyes and other things. 12. Not putting money in a parking meter and getting a parking ticket. What do you guys think? If you don't put a dependent, exactly. What about 13? Rolling a 6-sided die and then rolling the die the second time so that the sum of the 2 rolls is 5. So you want a sum of 5 on the 2 dice. What do you think? Dependent, definitely. Because if it is 2 on the first die, you need 3 on the second one. So you see, you need a 3 plus 2 to make it 5. If it is 1 on the first die, it's going to be 4 in the second one. If you have 6 guys on the first die, you will never get, a sum of 5. So they depend on each other. Okay, here's another one. I'll make it up now. Drive a BMW, get into a car accident. So event A is driving a BMW. Event B, getting into a car accident. What do you guys think? Dependent or independent? Why independent? I think they are dependent. Let me tell you why. When you buy a sports car, you don't buy it, just to drive, below speed limit. You're going to drive it at the speed. And usually, just when you speed, there is a likelihood that you will get into a car accident. This is considered a sports car. So there is some kind of dependency in there. And I think there is data that shows that events are dependent on most cases. Okay, so this is just examples of dependent and independent events. Okay, let me go back to the handout. A few more things. All right. Okay. Let me just make some conclusion about independent events. Independent events. Okay, A and B. The probability of event A, given that event B occurs, if the events are independent, it will be the probability of event A itself, because B has no effect whatsoever on A. So probability of A given B will be probability of A. And probability of event B given event A, if the events are independent, it will be probability of B, because A will not impact B at all. So this is an outcome of independent events. And the other more important formula, guys, if 2 events are independent, if you find the probability of A and B happening together, it will be the probability of A times the probability of B. And I'm going to demonstrate to you guys that this formula is a valid formula only if the events are independent. You agreed with me that tossing a coin and rolling a die are independent events. They have nothing to do with each other. He's asking us, what's the probability of getting ahead and then rolling a 6? Well, let's list the outcomes of tossing a coin and rolling a die. What are the outcomes? You could get a 1 with the head, 2 with the head, 3 with head, 4 with head, 5 with head, 6 with head, 1 with tail, 2 tail, 3 tail, 4 tail, 5 tail, and 6 with tail. Can you guys count them for me? How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have a 12 here. What is the probability of getting ahead and rolling a 6? Where do you guys see how many outcomes have a head and a 6? There is only 1. So 1 out of 12. This is the probability of getting a head and a 6. But what the formula says here, instead of doing the coin and the die together, you can do them separately. So here it says That would be the probability of a head times the probability of getting a 6. What is the probability of getting a head, guys? You know, when you toss a quarter, what's the probability of getting a head? Can someone answer this? 1 out of 2, great. And what's the probability of getting a 6 when you roll a die, guys? 1 out of 6, excellent. And you guys multiply the two fractions together, what do you get? 1 times 1 is 1, 2 times 6 is 12. Here you go, match. If the events are independent, guys, and if I asked to find the probability of the two events happening together, it's just find the probability of the first event, probability of the second event, and multiply them. We're gonna do the last example on this, and then we will stop there. So there's one more example and we'll be done for today. Example. The probability that a knee surgery is successful is 0.85. So that's the chance of success of the knee surgery is 0.85. Here's the first question, guys. What is the probability that 3 knee surgeries by 3 different patients are successful? Okay. You have 3 events here, guys, not 1, 2 events. First knee surgery, second knee surgery, third knee surgery. What do you think the probability of all 3 will be successful? Now ask yourself, first of all, a question. Are the events independent? Yes, they are, because these are 3 different patients. They're doing 3 different knee surgery, probably by 3 different doctors, but we know the chance of success is 0.85. How would you figure out the probability that all 3 surgeries successful? So we need success in the first one, success in the second, and success in the third. Does anyone have the answer? What do you think? It is probability. First surgery, success. Second surgery, success. Third, success. Any input, guys? I know how to do it myself. Yes, I got it's 85% for the first surgery, 85% for the second surgery, 85% for the third surgery. They are independent events, just multiply them, guys. Exactly. So let's do the math. (0.85 raised to the power of 3). And I got 614. Usually in the book online, you'll be asked to round to 3 or 4 decimal places for probability. You might be asked also to change the probability to a percent. If you change this one to a percent, it will be 61.4%, guys. Oops, right here. Okay, now I'm gonna change this. None of 3 surgery is successful. What is the probability that none of the 3 knee surgeries are successful? I think if a doctor performs those surgeries and 3 patients and the 3 are not successful, he or she would go out of business. So the probability has to be very, very low. It will be extremely low. How would you figure this out? That is correct. I got an answer from my students. Okay. For the probability that none of the 3 surgeries are successful, guys, means the first one is not successful, the second one is not successful, the third one is not successful. What's the probability of a surgery not being successful? It's 85% for success, 15% for failure. So it will be 0.15 times 0.15 times 0.15. And let's do it, guys. You're gonna see it's a very low chance that this will happen. We don't want this to happen. That's why the chance is very low. And watch the answer. 0.003375. I'll do 3 digits. It's a very small percentage. And actually it should be like that because you don't expect a surgery success rate 85% and a doctor performs 3 surgeries in the same day and none of them are successful. The chance with this happening is only about not even 3%, guys. It's 3 out of 1,000. So it's 0.3%. That is, now why I was allowed to multiply because the events are independent. So this is what I'm trying to explain to you guys. When 2 events are independent and you are asked to find the probability of 2 events happening at the same time, you just multiply the probabilities. That should be, that's what I just finished with the first group. So that should be it for today.